Good morning. Thank you for joining me for this video. I am Mr. Ish. Today we talk about the derivatives of inverse trigonometric functions. Previously we talked about derivatives of the regular trigonometric functions. That would be an easier topic than today. Now when you look over here on the side, I have the derivatives already laid out to you for the inverse 6 trigonometric functions. I have them laid out to you in order of decreasing importance or decreasing frequency of you seeing such questions. If you look here on the top, the sine inverse, cosine inverse, and the tangent inverse are most important and most commonly seen. The last three on the bottom are least frequently seen, and I myself will have to admit that I don't have all of these memorized. The reason for that being twofold. One, you don't see these questions too frequently, so therefore you're not running through them as often as you would like, and it doesn't get committed to memory. And reason number two, there are not very many applicable functions or models out there which would rely more on the inverse functions versus the regular trigonometric functions which are more commonly seen. So the derivatives of these inverse trigonometric functions, while they may be important, they're just not as commonly seen. But still, it is a topic we need to address. I'm going to start by showing you quick derivations of some of these inverse trigonometric functions before we actually look at some specific examples involving these functions. If you look over here at the very first one, the inverse sine, you know, just generally, when we're looking at a function like say f of x is equal to sine x, and you know when you do the inverse calculation you flip the letters around, and you can look to my video on the inverse functions regarding that. And you know f of x is the same thing as y, so you're saying y is equal to sine x, but then when you flip the letters around, given that you have a domain which allows a one-to-one function to be established, given a restricted domain, you can show that sine x is indeed a one-to-one. It's not one-to-one over its entire domain, but when you restrict the domain to like minus pi over 2 to pi over 2, it becomes one-to-one. But anyhow, within that restricted domain now, if you switch the letters around, you get x is equal to sine y, and then you know over here you would solve for y. Y would equal to inverse sine of that x. But the function you want to be looking at over here, or the format you want to be looking at over here, is this. And it's a topic that, now that I'm going to show you the derivation of some of these, it's a topic I haven't talked about, and it's a topic about implicit differentiation. Implicit differentiation is one of those topics where you have to be familiar with. Up to now, if you think about the videos I've presented on derivatives, I've always given you a format where y was equal to something and that function was already solved out for you and you were just deriving it. But sometimes you're unable to present a function in that explicit manner where y is equal to something, and sometimes you have something where x is equal to something instead, or you don't have the equation solved out in terms of y. But look over here, it's not solved out in terms of y. Y is not equaling to anything here, but y is actually attached to something. But assuming we knew how to do the process of implicit differentiation, I'll just proceed with that way. And when we learn about implicit differentiation, you can come back and review some of these derivations over here. But you would do the implicit differentiation by doing the derivative of this entire equation. You see how it's kind of different than what I've been talking about, the polynomials and the trigonometric function. This is implicit differentiation. When you implicitly differentiate it, you'll have some extra things you'll see over here, and it'll be kind of different compared to what you are familiar with so far. But don't worry about it, I'm just showing you how the formulas are derived. When you solve over here for these individual derivatives, x becomes a 1, and the sine y becomes a cosine y, because the derivative of sine is a cosine, derivative of sine y is a cosine y, and you have a dy over dx. When you solve for this derivative dy over dx, you take cosine y on the other side, you get 1 over cosine y. 1 over cosine y. Now if you think back to the Pythagorean formula, sine square x plus cosine square x is equal to 1. If you actually solve here for the cosine square, what do you get? You get cosine square x is equal to 1 minus sine square x, and you solve for the actual cosine x. Cosine x is equal to square root of 1 minus sine square x. Imagine if the sine square x is an x only. You basically get 1 square root of 1 minus x square. You see this square root of 1 minus x square is equal to your cosine x, or cosine y for that matter. Now you just substitute this right over here in place of this cosine y over here, and you get the derivative dy over dx. This is, remember, implicit differentiation. You get 1 over square root of 1 minus x squared. This right over here represents the derivative of the inverse sine, because we were looking at the inverse sine over here, weren't we, right? Now look over here, it matches exactly what you have over here. So using here the process of implicit differentiation, we can look through these. So you have to look through these via the process of implicit differentiation. Remember, it's different from explicit differentiation. We've been doing all along explicit differentiation, where I've always presented you examples of y is equal to and whatever it was, and we've been calculating the derivative of this. Here you didn't have an equation over here where y was equal to something, because it was not solved in terms of y. There are some equations out there you cannot solve in terms of y, simply because it's just impossible to solve for those equations in terms of y, unless you had some sort of computer software program which did it for you, a computer algebra system. But in those situations where you cannot solve an equation in terms of y, you have to use implicit differentiation. This is what it looks like. But I've shown you what this sine to the minus inverse sine derivative is, and it's over here. I'm going to show you here up to cotangent, inverse of cotangent, and we'll stop in terms of deriving part. Then we'll go to actual examples. These ones right here on the bottom are just not as importantly seen. Now if you look over here down here, I have a plus and minus 1 because I put these both in the single formula. If you're looking at the inverse of secant, it's positive 1 divided by everything you see in the denominator. If you're looking at the derivative of the inverse cosecant function, it's minus 1 divided by everything you see over here in the denominator. And you can look over here, inverse of sine is that, inverse of cosine derivative is the minus 1 over that, inverse of tangent derivative is 1 over 1 plus x squared, and the inverse of the cotangent function derivative is minus 1 over 1 plus x squared. These are sometimes not easy to memorize, and it's nothing wrong for you to utilize a reference sheet, and I have a reference sheet right over here. There's nothing wrong with doing that. Now let's look at the derivation of this. If you know that y is equal to f of x, which is equal to your cosine x, and you were to flip the letters around because you had restricted the domain of the cosine function, if you restrict the domain to 0 to, let's just say pi, 0 to pi, you can convert this into a 1-to-1 function. From 0 to pi, cosine has a 1-to-1 function. If I remember correctly, this is right. But if you switch the letters over here, you have x is equal to cosine y. You can stop over here because you can also take this and say y is equal to inverse cosine minus 1 of x, and here you've actually solved for y. But we have to actually solve for the inverse trigonometric function of the cosine and its derivative, so you'll do implicit differentiation over here. You'll do implicit differentiation. We'll be talking about that in one of the future videos. It's not a hard technique, but it is not entirely easy also. When you do the derivative of this, you split everything up. Derivative of x and the derivative with respect to y of this cosine function. When you do derivative of x, you just get a 1. When you do the derivative of cosine y, you get a minus sine y dy over dx. And in these implicit differentiations, you're always solving for this dy over dx term. Dy over dx is equal to, now look over here, minus 1 over sine y. I just took the minus and I put it here with the numerator. It could be here with the numerator, it could be here on the side, it could be here with the denominator. It's all good. And now let's, in a very abbreviated format, look at that Pythagorean trigonometric identity. Cosine square, or you can say sine square plus cosine square x is equal to 1. Solve for one in terms of the other. Well, you get, we're going to have to plug in the sine over here, right? So solve for the sine. So sine square is equal to 1 minus c square, and sine is equal to square root of 1 minus c square, or 1 minus cosine square. And if you imagine cosine here at a value of x, you get 1 minus x square all in a square root. When you replug this back in, you get a minus 1 over square root of this right here. You plug it back in here in terms of the sine, 1 minus x square, and you are done. And this x squared needs to be a little improved in appearance, and you get exactly what you see over here. The derivative of the inverse cosine function is minus 1 over square root of 1 minus x squared, and you can derive it using implicit differentiation. I want to go through the derivation of these two before we look at examples. The examples are actually not hard at all. The deriving part is more difficult because you have to do implicit differentiation, and these two you never have to even bother deriving them because they're too infrequently seen. For the tangent function, if f of x is equal to y, because these are synonymous and it's equal to tan x, and you know by restricting the domain you can make, and because the tangent function is always embedded within vertical asymptotes, you always have some form of a restricted domain, and it remains, or it can become one-to-one. Remember, most of these functions, trigonometric functions, are not one-to-one because they're cyclical functions. They keep repeating. So you can have repeat points coming up, and you can have range duplication. When you have range duplication, you lose the ability to demonstrate a one-to-one function. One-to-one functions are the ones which can have an inverse. But when you have range duplication, you lose that one-to-one ability. But when you restrict the domain to a specific set of points, you can bring in that one-to-one ability, and you can eliminate the range duplication, and you can start showing that your function, which before was not having an inverse, can now have an inverse. If you restrict the domain of this to its vertical asymptotes, and you can see graphically how that appears in my previous videos, and you flip the letters around, you get x is equal to tan y. This right here is the equation you'll want to implicitly differentiate. But if you were to solve for y, you would say y is equal to tan minus 1 of x, and here now y would actually represent your inverse function. You know, I have shown you all of this in my inverse function video, the general inverse function video, that this right here is a symbol for an inverse. If this is the regular function, this is the inverse function. And you know, the interesting thing about inverses and the general functions is that their domains and the ranges exchange with one another. The domain and the range of this would be flipped over here. The range would become the domain of what it was, and the domain will become the range of what the other one was. They'll flip. Let's get back to subject over here. We have to do implicit differentiation of this equation. Implicit differentiation. So you'll do d over dx of this entire equation, because you have not solved this in terms of y. You just have an equation. You're doing the derivation of all of this. And we will talk about implicit differentiation in the near future. So you'll do a derivative of x, and then you do a derivative in terms of y, because here you don't have a x, you have a y. This is a y over here. The derivative of x is just a 1, because you know this is x to the power of 1. You bring the 1 over here, you get x to the power of 0. You retain the 1 only then. The derivative of tan, as you know from the previous video, is secant square. But here we're dealing with y, so we have to put y over here, dy over dx, and you're solving in here in terms of dy over dx. dy over dx is equal to what? 1 divided by secant square y. Now think about the Pythagorean identity, the trigonometric identity, where I'm going to abbreviate now only. Tan square x plus 1 is equal to secant square x. We have here secant square y. So imagine you can substitute all of this over here, and what do you get? You get 1 over tan square y. We're using y because our variable is y plus 1. This is what it substitutes to. If imagine this is an unknown, the unknown can always be represented as a what? As an x, right? X squared plus 1. And you get your derivative of this inverse function. This right here is a 2. And look over here. The derivative of the inverse tangent function, you can look right over here, right? The inverse tangent function is 1 over 1 plus x squared, and that's exactly what I get. By means of substitution, and by means of implicit differentiation, and by means of recognizing a trigonometric identity, which you could have substituted. It's laid out here in front of you. I know we haven't talked about implicit differentiation, but when we do talk about it and you come back to this video, you can see the derivation of these four. I'm not going to talk about these two because it's unimportant. Let me show you the cotangent inverse function derivation next, then we're done in terms of this, and then we can go to the actual questions. The cotangent inverse function derivative will follow the similar example as that of the tangent inverse. Just like these two had a very similar derivation process, but you will see f of x is equal to y, because these are synonymous, is equal to cotangent of x. If you demonstrate that this is a one-to-one function by restricting the domain, which you can flip the letters around then. X is equal to cotangent and y. Remember, you're only flipping the letters around because that's the way you determine the equation of the inverse. When you flip the letters around and you solve for the new y, you show the equation of the inverse. So let's show you that y is equal to now cotangent minus 1 of x, and you know y here will now represent inverse function. Cotangent minus 1x. Anyhow, this right here is the equation you want to use for implicit differentiation. It's not solved in terms of y, therefore you have to use the technique of implicit differentiation. You'll do derivative of this entire equation, and then you'll start solving it out. Derivative in terms of this x is equal to derivative here in terms of y because you have a y on this side, and then dy over dx. Remember, I might explain things slightly different than what textbooks might show, but this is how I've learned it, and this is how I find it. My way of doing it is a little perhaps unorthodox, but I find it to be easy and it sticks better. Textbooks can get a little too theoretical and you end up losing the practical value. You do the derivative over here, x becomes a 1. The cotangent derivative, as you remember from yesterday's lesson, is a minus cosecant square, and we have to use y because we're using the y variable, dy over dx. You have to solve here for dy over dx, derivative of y in terms of derivative of x. You get 1 over, let's say minus 1 because you have a minus, cosecant square y. Now you have to think back to another trigonometric identity, one of the other Pythagorean ratios. Let's abbreviate, actually maybe not abbreviate too much. Cotan square x plus 1 is equal to cosecant square, I'm not putting the variables, well let's just put them in, cosecant square x. You see this Pythagorean trigonometric identity? Well, you have to look at this in terms of that. If cotangent x is a variable, you can say x square plus 1 is equal to cosecant square x, and you can just take this entire item and substitute it right over here, and what do you end up getting? You get minus 1 over x squared plus 1, and this right here represents your derivative of the inverse of cotangent x function. So you can see minus 1 over 1 plus x squared. I'm writing x squared plus 1, but order does not matter in terms of adding. 1 plus x squared is the same thing as saying x squared plus 1. The answer is still good and the answer is still same. These ones over here, I will not talk about the derivative of them. I'm showing you the derivative of them. I'm not going to talk about the derivations of them. It's not important to get into that. But you can see everything is laid out for you over here. An interesting topic, but not an easy one. But in terms of the actual questions we see next, you'll find out it's not that hard at all. It'll just involve substitution, you'll see product rule, chain rule, and you'll see the quotient rule, all of that. Except instead of dealing with the regular trigonometric functions, we're looking at the inverse. And remember, the regular trigonometric functions are more common and more important, and the inverse trigonometric functions are less commonly seen, therefore they are less important. So for the rest of this video, I want to present an adequate number of good examples. And I've made space over here and I've erased those derivatives of the inverse trigonometric functions. It's fine. As needed, I'll put them here on the side. And I also have my sheet over here for consulting if needed for the various derivatives. These are some of the derivatives that I have not committed to memory because I've not seen these too commonly, so out of less practice or less habit, they don't end up getting committed to memory as easily as some of the other derivatives. But let's focus here on the question. We have a 2 over here, a coefficient, and we have a function over here. So don't make the mistake as thinking that we should be using the product rule over here, because you could technically push this coefficient outside and then view this as just a chain rule in effect. Look over here, if we push the 2 outside, we get 2 derivative, and then we're just doing tan minus 1 x cubed. And now you know definitely you have a composite function right here, and you have to do a substitution. If your u is equal to x cubed, then f of u must be equal to tan minus 1 u, right? The inverse tangent in terms of that u. So now you actually have to use the chain rule over here, and by eliminating this coefficient and bringing it outside, we're not doing the product rule because we're not viewing this as a separate function in addition to this. You just end up complicating the question that way. So we have to use the chain rule over here, so we have to start writing the template out. So derivative with respect to u, you can have a tan minus 1 u, and then the derivative of that u with respect to its variable is an x cubed. Easy. Let's start calculating these out. What's the derivative of tan inverse tangent function? It's 1 over 1. It's 1 over 1 plus x squared, but you can't write 1 over 1 plus x squared because you have to use u over here. 1 over 1 plus u squared. I just flip the letter x to u because I'm doing everything in terms of u. What's the derivative of x cubed? It's 3x squared. If you bring this with the 2, you can say 6x squared. And then you know it's all going to hit the numerator, and in the denominator you'll have 1 plus u squared. But now you got to resubstitute back the u value, and you know what that u value was. It was x cubed. You'll have 1 plus x cubed squared, which is x to the power 6. Over here we are having x cubed, which was originally substituted for, and now you're resubstituting back, but it's u squared. So x cubed to the square becomes x to the 6, and here's our final answer. 6x squared divided by 1 plus x to the power of 6. So the derivative of this function is that? Good question. Let's look at some more. So when we're looking at this question next, we see we have two trigonometric functions inverses, but they are in their product relationship. So we have the product rule kicking in over here. We don't have any composite functions over here, but we have the product rule. So we have to now recall back what our derivatives are. The inverse sine function has a derivative, and you know it happens to be 1 over 1 minus x squared. Now let me see, I was doing this out of memory, if I'm actually right. Let me bring out my cheat sheet. So it's, yep, it's this 1 divided by square root of 1 minus x squared, and then the cosine is going to be minus 1 over square root of 1 minus x squared. Remember, you don't have to memorize these, nothing wrong with using a sheet, nothing wrong with that. We have the product rule kicking in over here, so we have to use a product rule template. The g function, here's my f function, my g function. The g function original is going to multiply by the derivative of the f function, which I have to still calculate, followed by a plus sign, and then the original f function is going to multiply by the derivative of the g function. And in this next step, we're going to bring in those derivatives. So the original g function here is going to multiply now with the derivative of the sine, which is what? 1 over square root of 1 minus x squared. You know this is multiplying, plus the sine derivative of cosine is a minus 1 over square root of 1 minus x squared. Now we just have to write everything in a proper finalized answer, and we're one step away from completing. Look at this minus and look at this plus. You'll convert this plus into a minus, and you can put everything in a fractional form. Cosine minus 1 of x divided by square root of 1 minus x squared. This minus, see this minus 1 hits with that positive, and you can get sine minus 1 x over square root of 1 minus x squared. This right here is a good answer. If you wanted, you could write all of this under a single denominator and just write this once, because they have the same common denominator. You can just marry them together. I won't do that, but you could have just write in a single large denominator with only a single radical here on the bottom, and both on the top in a minus relationship. But this right here is a good answer, and we're done. When we look at this question over here, we are seeing an inverse trigonometric function of the cosecant, but we're seeing two functions being multiplied with one another. So we know we're dealing here with a product rule, and you know you have an f function here and the g function over here, and all we have to do is very quickly recall using our cheat sheet, because I don't have this committed to memory, what the derivative of this inverse trigonometric function is. The derivative of cosecant minus 1 to the x is a minus 1 over square root, and we have an x over here. And let me refer to my sheet, I get a x squared minus 1. It's not an easy one to remember, because some of these things can be pretty tricky. But given that template, now we proceed. We'd use a product rule template over here. The g function over here, which is your original, multiplying now with the derivative of x with a plus sign. And now the original f function, which is x now multiplying by with the derivative of this inverse trigonometric function, which we have to see. And in this next step over here, we're going to actually bring in the derivatives. The derivative of x is just a 1, so we have an easy route over there. The derivative of this right here is exactly what you see over here, multiplying by minus 1 over x square root of x squared minus 1. When you bring everything together, you get as your final answer cosecant minus 1 minus, see this minus 1 is hit with this positive to give you a minus, then you have an x on the top, and you have an x square root of x squared minus 1. Now you might be thinking, well, should I cancel these out or not? Because technically you shouldn't. If you look at the formula, and I didn't bring this up, these are absolute value of x's. You can't just simply cancel out an x with this absolute value x. I just didn't talk too much about this absolute value, because some books do, some books do not. On here on my reference sheet, the formula which is given for the secant minus 1 inverse and the cosecant minus 1 inverse, depending on some textbooks, is exactly as I mentioned before, plus and minus 1 over, but here you have an absolute value x multiplied by x squared minus 1. So if you bring an x over here and you're dealing with an absolute value, they're technically not the same. You see this x and absolute value are technically not the same, so you can't just cancel them out. But it just basically depends on how the textbook shows you. Here I didn't cancel them out simply because of this technicality here. We have a bare naked x. Here we have an x within an absolute value. As you can see in my very first image of this video, I didn't mention the absolute value, but in some reference sheets you have an absolute value showing over here, so you don't want to just arbitrarily cancel things out over here. Just leave this as your final answer and you should be fine. Okay, let's grab our attention and look at this question over here. We have a derivative of this function. We have to calculate half inverse secant of x squared. You know, we're not looking at a product of two functions, and we have a coefficient over here that can very happily come out here on the side, and we would be just looking at a single function, but it would be a composite function, so we have to use a chain rule over here. Looking back to what I previously mentioned with the previous example, let's put the derivative over here of this inverse secant function using this other formula with absolute value of x over here, because in some books you can have an absolute value, in some books you won't have this absolute value, and x will be naked over here. But let's just use this version of the formula. You'll have an x squared minus 1. So we have to use that specific template over here for this when the derivative of this will come into play. But again, we have a composite function, so we'll have to do a substitution. If u is equal to x squared, then f of u must be equal to secant minus 1 of u. And now we shall begin. And there might be a little technicality which might arise over here, but let's see. Derivative now with respect to u, and we are putting in our substitution, and then we have du with respect to x. We have an x squared. In the next step, let's see what happens. We have a 1 over 2, and let's look over here at this x squared. The derivative of x squared is just a 2x, so we can bring that first. Now let's look over here. When you open this up, you get a 1 over, and you know u was equal to x squared, so you have a u squared minus 1. But what do we do with this absolute value over here? If this is a variable, this right here is equally just a variable, and we know this right here, u was substituted for this because u was equal to x squared. If u is equal to x squared, then what is x is equal to? The root of u. Therefore right here you must be considering a root of u, because it's half. I mean, it's like 1/2 in terms of the degree, the power of that. If that is 2, this is x to the power 1. So now we have to be a little wary of what we put over here. We're going to put a root u over here in absolute value. Root u. Because this x is equally as a variable as that. Now let's look over here. The 2's will cancel out. On the top we get left with just an x. On the bottom we get root u, or you can say u to the power of 1 over 2. Square root of u squared minus 1. Now all you have to do is resubstitute. We have to resubstitute exactly what u was, and u was exactly x squared. So let's do that. X over root of x squared, because u represented an x squared. See, u represented an x squared. We are resubstituting it. And here you have an x squared to the square. You get an x to the power of 4 minus 1. And that looks like a good answer. Remember over here, if u was x squared, you're doing a square on top of that, so you got your x to the 4th over here. So this over here represents a good answer, and the minor technicality we had was this part over here. So now that we have come up to this point, if you wanted to be slightly more fancy, you could actually have taken this one step further. You see this area in the absolute value. You have x squared to the power of 1, x squared to the power of 1 over 2, which is basically saying x squared to the root 1 over 2. But those things could have cancelled out. You could also say x over here in the absolute value of x, and then you'll have x to the power of 4 minus 1. You see, because this square, the exponent square is negated by the radical, the square root. The square is affected or cancelled out by that square root, and you end up with this. So this right here is also a good answer as well. So let's look at this question over here. We know we have a composite function over here, but it looks very similar to one of the examples we've already seen. You could technically push this outside over here and not make this into a product rule. All you would have to do is apply the chain rule, and that would be it. But we need to recall what the derivative of this cotangent minus 1, the inverse cotangent function is, and we know it's minus 1 over 1 plus x squared. Now let me just make sure if I'm indeed saying that right. When I look at my sheet over here, it looks like minus 1 over 1 plus x squared, so we're good. When we do this, we have to use a chain rule, and we have to use a substitution, because here, this is what is our composite function over here. In terms of this cotangent inverse, this right here is composite. If u is equal to 4x, then f of u is equal to cotan minus 1 of that u. So let's do this. So we have 3 we've brought out. Derivative in terms of the u, you know we're doing the chain rule over here. Cotangent minus 1 of that u, and then derivative of u with respect to x. We get a 4x over here. Now we have to do the individual derivatives here and here. Bring everything together. 3 will multiply by the derivative of this, which is just a minus 1 over 1 plus. Now don't make the mistake of putting in x squared over here. You have to put u squared because we're right now looking at things in terms of u. The derivative of 4x is a 4. You could essentially combine all of these coefficients, 4, minus 1 and 3, and you can get a minus 12. And here on the bottom you get 1 plus u squared, but you have to resubstitute back what u was. You'll get a minus 12 over 1 plus, what was u over here? It was 4x, but it's 4x to the power of 2, which is what? 16x squared. So you'll get minus 12 over 1 plus 16x squared, and this right here would be your final answer, and you would be good with this final answer. It's right. This right here will prove to be an easy question once we can recall what the derivatives of these are. And you're not having a product rule, you're not having a quotient rule, you're not having a chain rule apply, you're just having a derivative of two separate items. Basically a derivative of a polynomial-like expression, basically, that's what you're seeing. The derivative of cosine minus 1 and is a minus 1 over, let's see, x squared minus 1, or is it 1 minus x squared? Let me bring out my cheat sheet over here. It's a 1 minus x squared. 1 minus x squared. 1 minus x squared. And then the derivative of the inverse of the sine is just the same except it's a positive 1 or 1 minus x squared. Now these are they're mentally confusing to remember, therefore I never bothered remembering them. But let's plug these in over here. You're just going to separate everything out. You're going to do a derivative of the cosine minus 1 x, and then you do the derivative of the sine minus 1 x. It's not a difficult question. You just plug these things in. What's the cosine? It turns out to be a minus 1 over square root of 1 minus x squared. What's the sine derivative? The inverse sine derivative, it's 1 over square root of 1 minus x squared. Now if you look at this, you see similar terms which are minusing from each other. Like you can say a minus 1, positive 1, and everything zeroes out and your final answer is 0, and you would be good. What this essentially tells you that basically at that specific point on the curve, the instantaneous rate of change will be equal to 0, meaning you'll have no rate of change at that specific point. If you were to determine the slope of the tangent line of this curve at a specific point, you'd have a slope of a 0, which you know means a horizontal slope, meaning a flat line, a 0 line, and the tangent line would essentially represent a slope. Y is equal to mx plus b, right? The tangent line would have the equation y is equal to 0x plus b, which tells you what y is equal to b. Most likely your tangent line to a specific point on this curve will be just a horizontal line at that specific point. A horizontal line with a flat aspect to it, having a slope of 0, meaning no rate of change at that specific point. But we're not talking about all of that, we're just looking at the derivative aspects of inverse functions here, and that's what we're showing you. Let's keep looking at some more examples. Okay, when we're looking at this, we're looking at a function over here. You can view this in a different number of ways. You can actually view all of this right here as your f function, and this here is your g function, which is of course a composite function because you have a 2x. Or if you want, you can take this 2 and bring it out, and that's what I'm going to do and view it that way. I'm going to view the question as d over dx times x, then cosine minus 1 of 2x. So now I still have the product rule kicking in over here, the product rule, but I'll also have the chain rule kicking here because I have a composite function. And if you remember very quickly, we're looking at the inverse cosine, so we have to have a template for that. The template for our inverse cosine function, I will erase this over here and I'm going to put it for the derivative of a cosine minus 1x is going to be a minus 1 over, again I'm referring to this because I forget what's on the bottom, minus 1 over square root of 1 minus x squared. That's going to be my template for the derivative of that. So this is what I'm looking at over here, so I have to use the product rule and the chain rule. So let's start doing it. Let's bring the 2 out as we have and proceed from there. We're going to use the g function and the f function. The original g function, cosine minus 1 of 2x, multiplied by the derivative of the f function plus the original f function multiplied by the derivative of the g function, cosine minus 1 2x. But this is exactly here where I would want to have put in the chain rule, and I want to do that. If u is equal to 2x, f of u is equal to inverse cosine of u, and you'll see that right here. My substitution is u equals 2x. U is equal to 2x. Therefore, f of u is equal to cosine minus 1 of u. Alright, so let's do that. Cosine minus 1 of u, and then du over dx is equal to not equal to, multiplying with 2x. Now let's do the actual derivative parts, and all of this is multiplying by this 2. So 2 times cosine minus 1 of 2x times the derivative of x, which is just a 1, so we don't have to do anything there, plus x times the derivative of this is minus 1 over 1 square root of 1 minus, let's be neat over here, and this x will get replaced with the u because we're looking at u's over here. It'll be minus 1 over root of 1 minus u square. And the derivative of 2x is just a 2. Open things up. 2 times that is a 2 cosine minus 1 2x. Minus 1 times 2 times x times that 2 is a minus 4x over root of 1 minus u square. We have to substitute, and if you want to take this another step you can, or you can just choose not to even do this fraction algebra right over there. Let's do the resubstitution. We'll get 2 cosine minus 1 2x minus 4x over square root of 1 minus, what was u? It was a 2x. So 2x squared is a 4x squared. 1 minus 4x squared, and we are done. And it'll be right. For this video now on our inverse trigonometric function derivatives, this right here will serve as our very last question. And I'm looking over here at a rational function, so I know I have the quotient rule applying. I have a composite function over here, so I know I have the chain rule applying. That's alright. Quotient rule and the chain rule can be a messy combination, but that's fine. And we have an inverse trigonometric function with regards to tangent, and we have to recall what that is. The derivative of the inverse tangent function is equal to 1 over x squared plus 1. Yes, it's 1 over x squared plus 1, or you can say, or 1 over 1 plus x squared. It's the same thing. Quotient rule template, you're gonna do the g function, tan minus 1 x plus 1, and here's my f on the top and g in the denominator, multiplied by the derivative of the numerator x squared plus 1, which is my f function, minus the original f function multiplied now by the derivative of the g function. But let's bring in our substitution over here, because we know our g function is a composite function. If u is equal to x plus 1, then f of u is equal to tan inverse minus 1 of that u. And that'll be exactly what we'll substitute over there. You'll get du in terms of tan minus 1 u, and then du over dx x plus 1. You'll see all of that. It's a little messy over here, but you can see it. All over the denominator, which is your g function, tan minus 1 x plus 1 square, because it's always over g square, isn't it? Now let's actually open things up in the numerator. We have the original tan minus 1 x plus 1 multiplying by the derivative of x squared plus 1, which is a polynomial derivative. Use the scheme, it becomes 2x, easy, minus this x squared plus 1 multiplied by the derivative of tan minus 1u, which you have right over there. It'll be 1 over x squared plus 1, but you'll say u squared plus 1 because we're using the u variable. And the derivative of x plus 1 is just going to be a 1. All over tan minus 1 x plus 1 square. Now let's bring this coefficient 2x over here on the other side, because it's always better to have it as a coefficient. 2x times tan minus 1 of its angle x plus 1 minus, now look over here, x squared plus 1 is on the numerator, x squared plus 1, and you have in the denominator u squared plus 1. But what did u represent? U represented x plus 1, so you have x plus 1 whole square plus that 1. What do we end up with over here? In the denominator we have tan minus 1 x plus 1 whole square. Now it depends on how gung-ho you all want to be. You could do a common denominator over here and make this over 1, get this common denominator, multiply this side, solve the part on the numerator, bring all of this down here on the bottom, or if you want you can just stop right over here and just say you're done, and you would be done. And this answer over here would not be a bad answer. If you had an x and y value for this question, a point which was on this function over here, you would plug in the x values here. This x value, whatever numerical value it was, you'd plug it here in places of the x's, and you'd solve this out numerically, and it would give you your instantaneous rate of change, which would represent the slope of the tangent line. The slope of that tangent line would be an area at that point where the tangent line would graze your function. When it grazes your function at that specific point, it would tell you exactly what the behavior of that function is at that specific point. Anyhow, with that slope and with these x comma y coordinates, you could get your equation of your tangent line, and then you'd be done in terms of the application of this question. But our purpose here was only to get the derivative using the derivative formulas for these inverse trigonometric functions. So pretty much this right here in a nutshell is what the inverse trigonometric functions are. You can tell they're not very hard, but their derivatives are difficult to remember because it can be confusing. But you don't have to remember them. Just use your cheat sheet and you're good. And that's exactly what I do. For these inverse trigonometric functions, I have my cheat sheet and I use them. Nothing wrong with doing that. I hope you enjoyed this video. I hope it was beneficial. Please keep watching my videos and stay tuned because I have many more coming in terms of the calculus topics. Remember, we're still talking about differential calculus. We have yet to start integral calculus, and that's a whole number of videos right over there. Please stay tuned and thank you for watching. Have a nice day. Bye.